Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and this is my continuing feature on the Math Lovers book. I'm not doing this every day like I used to. I started another feature about a week ago or a couple of weeks ago. I have a daily math problem solutions, which I'm interleaving with these. And I haven't done this, I think, in almost a week, but this is my next video on this feature. Today I'm going to talk about quantifiers. This is the second there's two extra ingredients to predicate logic versus propositional logic. This is in section 7.3 of volume 1. Section 7.2 is on propositional logic, also known as Boolean algebra. But predicate logic still involves propositional logic, but it's richer because it also involves predicates and quantifiers. Last time I talked about predicates. Today I'm going to talk about quantifiers. So what are quantifiers? Well, there's just two of them. And they're represented by the symbols upside down A and upside down E. And upside down A means for all. So when you say, I mean, it's probably best to just give you some examples, but I'll just tell you what they are. So the first one is for all x. Something is true for every value of your argument, which we're calling x, or your Boolean variable. The other one is called there exists, and that's the upside down E. And that just means there exists a single instance, maybe more, but at least one incidence of something with a property X. So anyway, I'll get into this more. I have four examples I'm going to go over. Hopefully this will help clarify what I'm talking about. So here's the first example. How would we translate the statement, all oranges are round? How would we write that in predicate logic? Well, the trick is when you use quantifiers, you have what's called a dummy variable. In this case, we call it x. We usually use x and y and maybe z for dummy variables. Maybe you've seen this in algebra. There's dummy variables under summations and some under integrals, or just something we're summing over. And you can kind of think of it this way. So, but first we have to kind of translate this into a more logical sense. So when we say all oranges are round, what we're really saying is that for all x, if x is an orange, then x is round. X can be anything, but as long as x is an orange, it has to be round. That's another way of saying that all oranges are round. In other words, everything in the universe that has a property that it's orange, and remember that's a predicate, that's a description, an adjective, then it's also round. So roundness is like a superset of being an orange. I feel like, and I've never seen in my life an orange that's not round. So this statement is pretty much true. So now to translate this into symbols, for all we just use the upside down A. So we start our logical expression for our senses for all x. That's upside down A with an x next to it, and then we put a colon. We're saying something is true for all x, and what's true for all x is that if x is an orange, then it's round. And remember that we say that x is an orange, we say capital O small x. I mean, if I said something like John is an engineer, that was kind of an example I was doing last time. That would write you use the letter E maybe for the set of things that are engineers. So you write capital E sub J. J is a specific thing, in this case John, but here X is a dummy variable, so we use X for it. But now what we're saying is that everything that's orange is round. That means that if OX is true, then RX must be true. We're writing the if then operator next in between them. So we have OX, right arrow, RX. That just means if X is an orange, then it's round. So that's just a kind of symbolic way of writing. If for all x, if x is an orange, then x is round, and that translates into more common English as all oranges are round. So I think now you get the idea. And I'm going to do three more examples. I think the next one actually is a little bit easier. How would we say ghosts do not exist? Or there's no such thing as ghosts. You probably heard that a lot. Most people, I don't think, believe in the reality of ghosts. I think there are some people who do. I don't. At least not the way they're depicted in fiction, typically. I do believe in spirits, but not ghosts. But I don't want to go into that. But anyway, how would we say this? So, same idea, but now we're using exist. And so to say that x exists, we will write upside down ex. And now we want to write the negation of that. We're saying ghosts do not exist. So, and it's probably better to translate this into English first. So another way of saying that ghosts do not exist is to say for all x, or no, there does not exist an x such that x is a ghost. That's just another way of saying that ghosts don't exist. Or, if you want to say anything doesn't exist, like unicorns don't exist. Another way of saying that is there does not exist an X such that X is a unicorn. And you can think of anything else that doesn't exist, like, I don't know, trolls or, wicked witches or whatever. I mean, put your favorite thing in that you don't think exists. But here I'm just talking about ghosts. So now we want to translate this to statement and predicate logic. We would write the not symbol. That's the funny, thing that looks like a minus sign, but it's got a little hook on the right. So we write that to the left of our upside down E. That means there does not exist. And to say there does not exist, we have to write, not exist X. So X is just a general thing. And then we put a colon next to that. And then they say capital G, small x. That just means X is a ghost. But there's no such thing as ghost. Therefore, there does not exist an X such a G of X. So that's how you would do that one. And we could do more complicated examples than these. These are pretty easy ones. But sometimes we end up with compound statements. So here, and these are more typical. These are ones you might see in math. So now we want to write the statement: every natural number is less than its successor. And that's true. I mean, every number is less than the number that's one bigger than it. Every natural number, 7 is less than 8, 54 is less than 55. That's pretty obvious, right? The successor of a natural number is the number that's one bigger than the one you started. And since the second number is bigger, that means the first number is less. I think that's completely obvious. But now we have to translate this into predicate logic. This one's kind of tricky. Because now we're talking about two different numbers, two different things. So we have to give two different variable names for them. We can write x for the original number, and we can write y for its successor. So now we have a statement, a quantified statement that's true for all pairs of natural numbers x and y, such that x is this first number, y is its successor. And if that's the case, then it means that x is less than y. So how would we say that? Well, we have to have a bunch of predicates now. So we have to have a predicate for being a natural number, and that one I'm writing as capital N. To say that x is a natural number, we would just write that as capital N sub x. Similarly, we want to say that y is also a natural number, so we have capital N small y. And now both of those things are true. So we have capital N small x, and then we have a symbol for and, the upper wedge, and then we have capital N sub y. That just says x and y are both natural numbers. We've still got a lot of work to do. And remember, we're quantifying these things. That's why I'm using double variables. And we're saying this is true for all x and y, so we have to start by for all x colon, and then we're also doing for all y colon. This is sort of like a double sum or a double integral. We have a doubly quantified statement here. So two double variables and two for alls. So then we're saying for all x and for all y, if x and y are both natural numbers, that's just the symbols capital N sub x and capital N sub y. And now there's another thing that has to be true. Y has to be the successor of x. And the way we write that is we write capital S, small x, small y. That's just a fancy way of saying x is the successor of y. So the successorship is another predicate, and this has two variables, two arguments, if you like. And remember, the way we're doing predicate logic, we put all the arguments to the right of our predicate. So we write that as capital S, small x, small y. But now finally, what has to be true? If all these things are true, if x and y are natural numbers and y is the successor of x, then it also has to be true that y is larger than x. And we can write that as capital L, small y, small x. Notice I switched the orders around just because we're mentioning y, second, I guess. I guess we're saying y is less than x. What am I saying here? X is a successor of y. That means x is bigger than y. Or another way to say that is y is less than x. Yeah, so successorship implies you're greater, and less than implies you're less. That's why we're switching around the order. But I think you can see that this pretty complicated line in the middle of this slide is the way to express this sentence in predicate logic. So this was a pretty complicated example. These things can get complicated, especially when we have more than one quantifier. Let's do another example. I think this is the hardest one here. How would we say for every natural number, there's a prime greater than that number? This is also true. Euclid proved this around 300 BC. He proves there's infinitely many primes, which is another way of saying there's no largest prime. And another way we can say that is that for every natural number, there's a prime greater. There's no largest prime. Primes can be arbitrarily large. So how would we translate this into a statement on predicate logic? Well, I think you can see we're talking about all natural numbers, so we have to have the quantifier for all x. And we actually have another quantifier here as well. We're saying there exists a y, exists a prime y. But now I'm being a little fancy here. I'm saying for all x, if x is a natural number, then there exists a y such that if y is prime and y is greater than x, and you write that symbolically the way I show on the bottom of the slide. Upside down a small x, that means for all x, colon, capital N small x, this means x is a natural number. So these first two parts just say for all natural numbers, and then we're saying if x is a natural number, we're writing if then, the right arrow. And now the part that goes on the right, the conclusion is that there exists a y that's upside down e small y colon. And now we're saying what's true. Y is prime. We were assuming that y was prime. So there exists a prime y that's greater than x. And so we say capital P sub y and capital G sub y sub x. That just means y is greater than x. So I think you can see this is the symbolic way to write the statement that there's infinitely many primes. You have to translate this into math. Math is all about proofs, and logic is kind of at the heart of math. I mean, everything you do in math involves logic and it involves proofs. You don't always have to write down logical expressions for what you're doing, but if you were going to program a computer to do this, you would probably have to do something like this at some point. And I'm pretty sure, I mean, AI is getting so advanced these days that maybe even ChatGPT can prove the Euclid's theorem that there's infinitely many primes. I wouldn't be surprised if it can. If you gave it enough information, it could probably spit out a proof on its own. AI is getting very advanced. And I'm getting a little sidetracked here, but a lot of people are scared about it. I'm not really. I'm kind of excited, actually. I think as long as we don't let AI become our slaves, it won't. As long as we use it to do what we want, then we're still dealing with classical computers. Things might be different once we start. We're using quantum computers because I think those can be conscious like us, but I don't think classical computers can because they always, return the same output, give them the same input. So I think classical computers can only hurt us if we let them hurt us. And like Hal said in the movie 2001, any problem he had was due to human error. So I kind of believe that's still true with computers and with AI. Anyway, enough of me preaching about all that. Anyway, that concludes my video for today on quantifiers. Thank you for watching. Long live math, and I'll see you guys next time. Bye.